So, this is going to be kind of a short stream, maybe an hour, if that. I'm going to clean off my desk a little bit, my little project work area, and I'm going to go through my project boxes, which they've got a bunch of stuff in them. I think one of the boxes, well, it doesn't matter. What I'm looking for is what's called either a photodiode or a phototransistor, and I just want to locate those. This idea about that I've been working on using this reverse bias of an LED, it's fine and everything, but evidently the photodiode or photodiode, it does the same thing, and it's a lot more sensitive, and it actually operates in a reverse bias region, I think, but it's just set up a little bit different. I don't know how they set it up, but anyway, I think that's what it does, and it's more sensitive. So why work on something that's just really not sensitive enough when you've got something out there that is, so I'm gonna do that. I'm just setting up my stream right here, and it's more or less kind of like a more or less not a very exciting stream, but maybe tonight I might work on the circuits. I was gonna build a whetstone bridge circuit, which really should be easy to do, but then I wanted to build the LED transmit circuit to transmit a modulated waveform across the carrier. And there was one video that I saw that what they did was they added bias to the waveform, and then they moved the bias up. I don't know if this was dealing with the reverse thing. It was in one of those demo videos. And they were showing, I'll just mention this, they were showing videos of how to do things with light, which, okay, it's fine. One of them was taking a tuning fork, putting it into the light beam, and the light beam just goes to a solar panel. The solar panel converts the electricity. That's fine and all. And, I haven't even done that yet. So, we're going to do some of this easy stuff. And then we've got the different types of photodetectors. And so we have to I want to check the response of them at various frequencies, and see what frequency range I can use them on. Because the information that I'm going to be getting could be anywhere from, it could be from audio all the way up to, say, maybe 1 megahertz. The thing with trying to get information off of a light beam is that the light beam has a crap ton of bandwidth. So you can put let's say a light beam carrier is like 500 nanometers, okay? And so normal radio situation, you would think okay, it's like 14 megahertz, and you've got an audio signal that's riding on 14 megahertz. An audio signal is only like 4 kilohertz bandwidth, okay? And we could even say it's 10, well, it's not really 10, it's like 4 or 5 or something like that. It's really small. AM radio stations, they have a little bit larger bandwidth because they use both sides, so it's like 8 kilohertz. That's audio. So it wouldn't make any sense to try and detect audio off of a light wave when the ability to detect a signal that is much higher in frequency off of a light wave is available. So in order for that to happen, you've got to have a detector that's capable of the response of the frequencies that you're trying to measure off the light wave. It only makes sense. So if I go, I'm gonna go to a website, and I don't even know if I have one. Yeah, I got a website, but I'm not gonna bring it up on the screen here. So we know, for example, let's say if we have a Lightwave that is 500 nanometers, and the resolution of the Lightwave is, let's say it's 25 nanometers, okay? So we want to convert nanometers to megahertz, because that's the easiest way to see how a radio signal, what kind of radio signals can you put in a space of 25 nanometers. Now the 25 nanometers, maybe it's actually 20, okay? That's a really good resolution, and it's 10 nanometers on either side. So maybe it's 20 nanometers on either side. So we're looking at 20, 25 nanometers, okay? So we go nanometers to, nanometers is actually a wavelength. So we want to convert nanometers to a frequency. So nanometers to megahertz. It's actually in the terahertz range. So it's like 300,000 megahertz. That's really strange, because that's the speed of light. What the fuck? What the hell? I make interesting discoveries when I do this shit. Okay, so the speed of light is 299, 792, and 458 meters per second. 299, 792, 458. 1 nanometer is 299, 792, 458, 000 megahertz. What the hell is that? That's the speed of light. Wavelength in nanometers, which is 1. That's really, really, really 0.1 nanometers. It has the same speed of light number and adds a 0.01 nanometers, so on and so forth. So the speed of light number, which is in 1 nanometer at the speed of light megahertz, goes down. It's almost like it halves when it goes to 2 meter. It goes in half. 99 is 18. Yeah, it's 1/2 of that speed. In all the other, measurements, 0.1, 0.01, they have the speed of light number. We're looking at 20 nanometers. We could actually, 10 nanometers does have a speed of light number in it. But we can't get down to that resolution. So let's just go ahead and put down 25 nanometers. I think the best resolution is like 18 nanometers. So we're going to take 25 nanometers, and we come up with, let's see, what is this number? It's 3 and a 2. It's 3 and a 2. So it comes up to, is this right? So there's 1,900,000,000 11 billion. 12 billion megahertz. Damn. 12 billion megahertz? Are you freaking kidding me? So if you divide a carrier frequency, you can have carrier frequency, you could have a higher carrier frequency running on a light wave, and that carrier frequency would have the bandwidth to carry all kinds of information. But 11 billion? What the hell? Because normally, like, we operate 14 megahertz. It's like the 20 meter band, okay? 20 meter. And we're talking nanometer, which is 10 to the minus 9 meter. 11 billion. Okay, 12 billion. So let's see. Let me just make sure. 600,000, 1 million, 10 million, 100 million, 1 billion, 12 billion. Oh, God in heaven. So 12 billion. Oh, wait, I need a calculator. Normally at 14 megahertz, you carry an audio signal. 30 megahertz, those are the HF bands. What if we went to 1 gigahertz? The cell phone bands are like 900 megahertz, okay? So they've got a certain bandwidth, and it carries a bunch of phones and stuff like that. That's sort of the high-low end of the information carrying stuff. It's 1 gigahertz, which is 400 megahertz, 900. It's like 1,000 megahertz. 1,000 megahertz. So if you take 12 billion, it's 1, 2, 12 billion megahertz divided by 1,000 megahertz. 1, 2, 3, 1, 2, 3. So that's 12 1 gigahertz channels. 12 1 gigahertz channel. So a gigahertz is 1,000 megahertz, and you could have, let's see, I don't know what the bandwidth is for that stuff up there, but it's what it is. It's 12 channels of 1 gigahertz, 12 1 gigahertz channels in a 25 nanometer bandwidth. So, basically, if we were an advanced civilization, my air must be dry or something. Damn. So, 12 1 gigahertz channels, okay, 1,000 megahertz, right? So let me go to typical 1 gigahertz bandwidth cell phones. Typical modern smartphone connects network, constant mobile frequency bands, rhythms, a single 1 gigahertz band, yada 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 yada. Mobile devices operate across low band under 1 gigahertz, mid band 1 to 7 gigahertz for balance, and high band 24 gigahertz. 4G LTE channel bandwidths usually range from 5 megahertz to 20 megahertz. 5G is 20 to 100. So if we're talking, say, 10 megahertz channels. Oh wait, that doesn't make any sense. Device actually represent a microwave or alter UHF signal common use for radio navigation, etc. It's not giving me the information I'm looking for. Oh, you know, I think so. Like, what would that be? Like one channel, one 4G channel is 10 megahertz. Channels on a 1 gigahertz network. There is no fixed number of 5G network. 600 megahertz for the number of channels depends directly on technology. Standard channels 5, 10, 15, 20 megahertz in a continuous 1 gigahertz block. This allows for 50 channels. 50 channels of 20 megahertz width. Utilizing a 5 megahertz width, translating to actually 200 channels on 1 gigahertz, 200. Wait, no. That takes up the whole frequency. That doesn't make any sense, though. Radios typically operate 1 megahertz to 16 megahertz. Well, I don't know. If I were to say, what did I say? Did I say 12 1 gigahertz channels? What's that calculator? Twelve 1 gigahertz channels, and each channel, say, it contains 12 1 gigahertz channels. Okay, let's just say, let's do this. Radio and microwave engineering, the amount of noise at 12 gigahertz depends heavily on the context, but the absolute baseline of thermal noise is, minus 174, I know that. Typically, high performance oscillators, 12 gigahertz oscillator, runs from minus 110 to minus 167. At a 10 kilohertz to 1 megahertz offset from the carrier. Minus 10 to 167. So if we use minus 150 as a baseline, let's see what this is at 1 gigahertz now. Room temperature, fundamental Johnson-Nyquist noise floor, 1 gigahertz bandwidth is minus 84. phase noise, referring to a specific carrier frequency. Noise is measured as phase noise. Example, a 1 gigahertz carrier with noise measured at a specific offset, like whatever the hell that is. Minus 120 dBc per hertz. Maybe I'm looking at minus 84 to minus 150. So anything above minus 150, yeah, but that's crazy. That's why I was thinking I need to make my environment cold. Because I've got to have a noise floor that's minus 150. Typical noise floors in radios are like, the good ones now, they're like minus 102, minus 110. That's a radio. Now, these radios, they've got a lot of circuitry in them for mixing and all kinds of stuff. Let's see here. Let's look up. I want to look up LT1028. And we're going to look up, let's see here. Operation amplifier section for quantum noise. The LT1028 is the lowest noise amp available today. Well, that was back in 2018. I've got a few of those. I used them when I was working at one place. Let's see. What is that? Is that a photodiode? Ultra low noise photodiode amplifier, right to the LT1028. Crazy. Okay, so this operating temperature is 0 degrees C to 70 degrees C. We need to be down colder than that. That'll be interesting if we can pop that baby in cold temperatures. Plus or minus 4 to 18. Low noise. What else? The PDF. That is there. Operational amplifier selection guide. LT28. Source R. But the temperature thing, okay, so we could use this as a secondary amplifier. So then we'd have to look at, let's go to the 2N 2819. Now the 2N 2819 is an FET JFET, which has a very sensitive input impedance. Crap, I just lost the page here. 2. Hello. Yeah, okay, 2 and 9. We are operating in state-of-the-art Now see this stupid AI is... Okay, I'm not gonna lose it. Nope, not gonna lose it. It's saying it's an NPN silicon power transistor. Yeah, okay, you're a POS. Okay, so next victim. Let's see here. What is this? Need a PDF. I want the status data sheets here. Where are you? You have to do multiple research. If you don't, you're not gonna get the information. And I'm telling you, it's like there's so much information out there now that comes from so many different places, you know. You wanna check on some multiple stuff here. Power transistor. It's not a power transistor. 28. Oh, there's a 203904. They're calling it a power transistor. Error, does not compute. Let's see, there's a 2N3904. But it's not PDF, I'm not interested in that. Visit site Aero Electronics. No, I'm not pressing and hold. You can... I swear to God, I can't find it. That's why I got a lot of this stuff on my computer already in my electronics section. I may have to look for it on there because I can't find it. Alright, that's what I'm gonna do. It shouldn't really take too long. Let's see. Electronic programs, manuals, circuits, stone bridge. Oh boy, hit a bunch of stuff somewhere. Where it is. Manuals, this is light programs, photo transistors. There's a manual here. Using phototransistor circuits. They have this one connected to an LM339. Non-inverting and inverting, and they're using a phototransistor. Phototransistors have a non-zero collector current known as dark current, etc. Yada yada yada. This is a very temperature dependent and is in the range of about 100 nanoamps at room temperature. A pulsating light is more easily detected since a changing collector current can be differentiated from a static background. Binary and linear. Binary looks at the presence of a light level and output a logic signal accordingly. Whether the light level is above or below detecting certain threshold. It's using a comparator. I don't need a comparator. No, this is not looking for. They're using it to turn lights on and off. This manual is no good at all. Makes a lot of sense, right? Oh boy. Manuals. Thought that somewhere I had a whole crap load of... Wait, is it? Stuff somewhere, but I don't know where it is. Music's pretty cool. Pulse width modulation. Detector files. What is this PDF here? This is receiver signal pulse width modulation circuit provides ADC function to increase sensors' dynamic range. That's interesting. What's this one here? It talks about a pulse width modulated signal. Modulation analysis. There's nothing there. Oh God, don't you touch that. Circuit ideas, circuits. Stuff I'm supposed to sort, which I haven't gotten to. IP21. What is that? Oh, that's the photo multiplier tube that I've got. 300 to 650 nanometers. Should bring up the webpage, but I'm too lazy. I don't really care about that because I'm not working with that right now. IP28, 583. Application to the study of quantum fluctuation. Frog's optic nerve, gas Kazuki. You don't know this. I'm not interested in the frog's optic nerve. I'm trying to find my specs for my transistors and stuff. What are those figures? Optics. Optical collimation. Spheres, photo multiplier tube. No. Wonder what these figures are. Telescope stuff. Oops. High voltage power supply, low voltage power supply, photon counting pulse conditioner. Input pulse from PMT. Yada, photoelectric photometer. This guy's using a PMT to do some crap. Oh, what's this here? Is this slit? I don't know what that is. Not a clue. Cool as Harry. How about this one here? Ah, found it. I should move these to transistor specs. Let's see. What if I grab those? I want to grab these and move this stuff here. I don't know what this is. That. I found the specs for a 2N222, a 3904. Data sheet to something. Laser supplies, an LM108, mission critical applications, photometer, resistors, yada 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 and yada yada yada. I don't know. I don't see the 2819. I'll have to go back and look for it. I'm just going to move these over to electronic programs. And let's see, what is the 3314? I think that's a signal generator chip or something. NPN transistor, basically 3904. Has an operating range of minus 55 to plus 50, or 150. And we got our garbage in. Wait, is it garbage in, and then we have our garbage out. Have a nice day. Let's see here. Where's my PDF? I lost it. That's high voltage. We're talking 40, 60 volts. 60 on a collector base. Collector emitter is a 40 volt. So this would be, and it's got that high wide operating range. Thermal resistance junction to ambient. Max is 200 degrees centigrade per watt. Let's look for frequency response. Small signal characteristics. Frequency at 100 megahertz, which is above our range. We're talking a minimum gain of 250 to 300. Output capacitances, input impedance at 1 kilohertz is 1 to 8K. It's fine. 1K input impedance, which is low. So when you have the when you use the FET, well, I think this would be like the LT28 would go into this. No. Damn, because that only goes down to 0 degrees. I gotta get into that FET. Alright, let's just go back here and see if we can find it. Once I find it, I'm going to save it. I think I found one. Okay, I think I found it here. N-channel JFET. It says you can use it as an RF amplifier, but yeah. Just scroll down through this really quickly. Well, it doesn't have a lot of information, does it? Where is the temperature range? Minus operating and storage junction temperature. Minus 65 to plus 150. Yes. We're going to save this page as. And that goes in my electronics section here. I didn't think it went down that far. So we've got a 2819. That's really all I need to know there. IGSS gate to source. Maybe that's a dark current at 15 volts is 2 nanoamps. We are I gate to source 15 volts, ambient temperature at 100 degrees centigrade. Are you kidding me? That is like hot. When you're hot, you're hot. No. When you're not, you're not. That current is 2 microamps. We're going to be operating, well, at 0 degrees C, minus 20. At 1 megahertz, I think there's a frequency response thing here. It says it's 2 to 6.5 milliseconds. At 100 megahertz, it's 1.6 milliseconds. At 1 kilohertz, it's 50 microseconds. Okay. Whatever those numbers are. I'm not worried about that because I can test that stuff easy. That's not a problem. Drain current, drain source voltage, drain saturation. 260 milliwatts. Damn. That's freaking crazy. That transistor's obsolete now. It's replaced by a 2N4416. And numbers are a little different, but in the spec sheet. Let's see if we can find. I want to find that one too and see what that says, because that's in the circuit program. And I may decide to go there. I don't know, I'm not feeling so happy. 2N4416. It's a lot of work to do this because it's... Alright, it says this is a metal can, but it doesn't matter. Minus 65 to 200. Voltage is at 30 volts. 30 volts, 300 milliwatts. Let's see. Yep. I'll just save this one, I guess. File. And that's in my electric programs. Okay, we've got that one. Now I'm gonna look up this LT1028 again. Oh, my phone is turned on. Yeah, it's on. I might be getting a message at some point in time. There's a PDF here. Let's see what this one is here. Here's another one. Linear technology, LT1028. Very low noise. 50 megahertz gain bandwidth product. Offset voltage 40 microvolts. Drift with temperature 0.8 microvolts per degree C. Voltage gain 7 million minimum. It says it can do the photodiode, but that's not where we're going to put it. This thing only goes to... okay, what's going on here? What the hell? This PDF says it goes down to minus 155. Why did the other one say... Okay, let's save this. Save file, save page as 1028 MB. Is there another one in there? Huh. The other one said 0 to 70 degrees C. I believe this one more. This is from the Linear Technology site. This is the PDF from the site that makes the amplifier. Frequency, voltage, noise density, nanovolts per microhertz. Well, up to 1 kilohertz. It's less than 1. Let me just go back down through here. Minus 65. Specified temperature range is 0 to 70 degrees C. Consult LTC marketing for parts specified with wider operating temperature. The temperature grade is identified by a label on the shipping container. So the numbers that they're giving me are basic numbers from 0 to 70 degrees C. 0 degrees C is like 30. Is 0 degrees C. It's not 32, is it? It's freezing. That's at freezing point. Let's go through this list. I'm looking for I mean, this thing is a crazy good amplifier, and I'm surprised. I wonder if they got. Did it show that in here? Oh, it's got all kinds of stuff in here. Typical total noise versus unmatched source resistance. We're talking nanovolts per microhertz. At 10 kilohertz, maybe it's like 100 nanovolts. Current noise spectrum, 10 to 10K. It's like less than, that's picoamps per microhertz. Now this is, so any noise that's on there is going to be coming from the power supply. Applications. Noise applications. Noise under test. Noise, current noise. I'm looking for that. What that photo thing is in here. Typical applications. Low noise, wide bandwidth instrumentation amplifier with a plus and minus input using two of them. And you can even use another one, a third one, to do the output. See, the problem with using, it's not showing the photodiode. It's an amplifier. Did I save this? Let's see, file. I must have saved it. Okay. The problem, what did I say? Is because the stuff that we're trying to measure, when I did this experiment before, something came across. It was like a Christian, I mean not a Christian, but a religious radio station just popped in out of nowhere. And all I had was an amplifier. Wasn't even using this. I think I was using the 741 and something else. I hesitate the use of op amps. So the way this would work would be the FET, the LT1028, and then the 2N3904. Now, with the whetstone bridge in front of the FET. Now I don't know. Okay, so what we're going to look at is, let's type. So we've got drain gate source. The gate is where the signal comes in. I'm not sure what the circuit there is. It's 2 and 28, 19. Photo. Diode. Yeah. Go to images. Okay, there's one here. Oh, they're using that one. It's on the end. So I want to save this one. Save image. This is pictures. This would be. LT1028 photodiode amplifier. Like, we could use that right on the front end. Oh, wait a minute, no. What is this here? got a different JFET in front of the LT1028. That's interesting. Let's see what's up to 75 here. I want to use that JFET in front of that photodiode. That's what I want to use. The NPN, the bipolar transistor, I use after the JFET. That acts more like an amplifier. The JFET would act like as a preamp, because we're measuring stuff that's down in the microvolts here. That's why we need a very sensitive setup. There's a photodiode. One must acquire. Here's another circuit file. Wait, actually, let me save that. Save image as. So here they're using a BF862. I don't know what that is, but it really doesn't matter. I can use any FET I want. I would just have to change the circuit accordingly, according to the input and output impedances. It says the JFET. Okay, so that's what it looks like right there. It's an N-channel JFET. One is the source. I should probably just take a picture of that. using op amps and bipolar transistors. There's two of them here. An LM386, that's a speaker transistor. So we've got something here. Looks like a modulation circuit. What is this here? Schematic of an all-band shortwave direct conversion receiver. Really? Remind you the DDS generators, solar stores, I don't care about that. Generator 0, generator sinusoid 0 to 60 megahertz, the remodeling grid can be selected. Principal scheme. Input signal from the antenna input circuit, not shown here. Enters the frequency converter performed on two identical field transistors. 2819. The input signal is supplied to the V2 shutter and the heterodyne signal from the external DDS generator to 600 millivolts. So I'm going to save this page. I can build this. It's not that much information. What I'm gonna do is grab this. I want this information. The work of the cascade BT1 and 2 transistor is similar to the work of a similar cascade on a 2 reclined transistor voltage, as well as on the second shutter of the 2 capacitor. You can change the result, or in this case, give a heterodyne signal for demodulation. By the way, changing the heterodyne voltage can be yada. Like one of them is your demodulation signal, the other one is your carrier signal type thing. You tune the carrier signal. Direct transformation. What the heck is the carrier signal? The load of the cascade is the resistor R4. It's R5. R2. R4 is a 1K resistor to 12 volts. Damn. This is easy to build. And they got it connected right to an LM386 to power a speaker. Are you shitting me? Only the Mother Russia have the information you need. C5 capacitor along with the R4 resistor forms the simplest NF filter. The suppressing signals of the total frequencies and the input radio signal. This is the only demodulated signal RF remains, which through volume controller R5 enters the UHR on the A1CCC G-gram, whatever that is. I want to build this. I definitely want to build this. This uses 2819s. Now, of course, these values. Okay, so he's got 100 ohms on the bottom of on the X2, and the X1 he's using 1 megohms, and these might be like shunt or filter capacitors down here at the bottom, and there's some more capacitors. He's got a capacitor filter for the power supply, like easy stuff. The receiver is assembled in the body from a faulty select of the SM24 channels from the old domestic TV. The body is shielded with 2 coaxial connectors used here to supply input and heterodyne signals. Installation is made on the dismantled board of SM-24 using the techniques of printing and volumetric insulation. Also, I discovered this interesting little circuit. But this is probably just gonna do like AM, and like I'm thinking I can connect my signal directly to my radio, because my radio's got sideband, it's got AM, it's got FM. That's what I'm thinking I'm gonna do. That's cute, huh? All right, enough of that BS. Oh, what is this here? This is that's the whole picture. I wanted to look for my photodiodes. That's what I'm going to do very shortly if I get a chance. Oh, I don't know if I can find that other circuit, can I? Oh, what's this here? Okay, there's a picture there. Let's see, save image somewhere. What else to save image? I've never had good luck with these oscillators. I'm just gonna go to an 888. Two-stage. The same one. So there's an FET preamp and an NPN transistor at the output. The output load is 220 ohms, which is good for the LT1028. Like, this is a very low level amplifier stage. You know, I wonder if I could use 2 FETs at the beginning. That I don't know. See, that's a high input impedance into this thing here. What does this say here? Nothing. What's this one here? This is interesting. FET principles and circuits. You've got 2 megohms, which is extremely high input resistance on this load, and a 3904. Let's see what this thing says. Shit's taking up slow for my taste. It's loading up on another web page. Oh, here's a photodiode circuit. K3PGP receiver. This is a typical JFET circuit to amplify the photodiode signal. Is this simply the photovoltaic voltage generated by the photodiode? My understanding is that this is highly nonlinear, since the voltage across the diode with increasing light level. At very low light levels, it is possible that the diode remains only slightly more than 0 bias. This is a ham radio operator working with light communication stuff. For an AC modulated light signal up to 3 kHz, I have been trying a discrete JFET circuit. I am sure this is not a transimpedance configuration, as in the op-amp implementation, which maintains 0 bias across the diode. I don't know what does that. Oh. Yeah, this is not... I don't know what he's doing there. He's connected the photodiode directly to the input of the FET, which I don't think you can do that because the impedance is going to be like really low. I mean, you could, right? But you would want some kind of input impedance there. Even, you know, what are you going to do, you know? Milliwatts per square centimeter, like 10 to the minus. He's trying to power this up a little bit. Is what he's trying to do, I think. Yes, very non-linear, not at all as linear as the standard transimpedance op-amp, where the diode is run at either 0 volts or at a fixed reverse bias voltage. And when that happens, usually the music goes away. The circuit is really only useful for detecting very low light levels. Light levels, mind you. This circuit. Yeah, I don't like that diode connected to the FET like that. Non-linearity might be a feature rather than a bug, etc., etc. It won't saturate, yada, yada, yada. Listen to this. Preferably run the photodiode in reverse bias mode to a negative supply rail to minimize capacitance. Well, maybe does this guy know what he's talking about? See, right here, the ground is on the anodes. It's running in forward bias mode. Did I save this? don't like that circuit. It's interesting because I'm thinking of using the photodiode. What if I look up? Let's try this here. There's one there. I'd like to see it to 2819 get used, but that's not negative bias. Working common source JFET amplifier. Is that going to let me save that image, is it? Shit. That is small. This is a rather informative web page. This one is a little different. This runs it in a current mode. There's a JFET up here, for whatever thing that thing is doing. I don't know. Photodiode here. Photodiode JFET amplifier circuit. LT something. Op-amp 07. Trans-impedance amplifier using a op-amp 07 and 5 gigohm resistors. That's rather interesting looking. .500 microvolts per lumens. Up 37. I don't have that LT1001. TLO81. Op-amp photodiode, I don't know what that crap is. LM339. Photodiode. This just turns on an LED. This would assume that the light level is like really bright, you know? Let me take a picture of this. And I'll just put this over here. I've probably done this before, but God knows where my stuff is. LW. I particularly like the looks of that. JFET amplifier circuit, etc. VM 5 mils. What is the value of VE? This particular circuit I like the looks of better because, well, there's really no resistance. Oh, this is one of the stupid ass web pages, huh? What's this here? JFET common source amplifier. Common source. I can't get it. Huh. That's interesting. 2 megohms, 0.01, 24 volts. Okay, so that uses 2K as an output. Oh, I think I'll save this. Spending a little bit more time on this, ain't I? JFET feedback amplifier. Definitely do not want feedback unless I'm creating a particular circuit myself, you know. Well, that's a different kind of common gate JFET amplifier. And it's AC equivalent circuit. The gate is grounded and external load resistor R is connected to the drain terminal decoupling capacitor. An equivalent AC circuit current. In an AC equivalent circuit, current source is connected between the drain and the source. However, since the drain and the source are input-output terminals respectively, GM-VGS appears between the input and the output. I'm not familiar with these types of circuits. This has a voltage gain. I just don't like it. I'm not comfortable with using that kind of a circuit. These are the more typical ones. That's a typical circuit right there. Oh, what's this one? Bipolar op amp? This is a JFET. What are you talking about? How to design a noise optimized transimpedance amplifier. Okay, I'll bite. That's not a bipolar amplifier. It's an LT28 bipolar op amp. Fine. What is this diode here? Is it any diode? What the hell? The op amp input often as significant capacitance, frequently source impedance is not resistive. For example, for photodiodes, it is usually approximately capacitive with a low series resistance. In these cases, I something varies with frequency, tending to dominate by voltage noise at higher frequencies and by current noise and Johnson noise from the feedback resistor at lower. Thus, because of the lower current noise, a J-foot input stage would generally be preferable at lower frequencies, and a bipolar input stage would be preferred at higher. J-foot input stage. This is a photodiode. I don't know what the hell this thing says here. V diode something. ID. Oh, it wants to be a stinker, don't it? Configuration 3. Some typical numbers here. You have to bear with me here. Because I am going to save this little stuff here. Come on. Well, it's going to be Yep, that's a basic JFET amplifier with the LT28 at the end of it. Oh, this one looks a little different. This has got plus 12 here. That's a photodiode amplifier, and it looks like it's operated in reverse bias mode. This is called a transimpedance or current to voltage amplifier. Okay. We use an LM741 UG to convert the small leakage current. That's a different circuit. When the LED is turned on, reverse current flows to the photodiode from the cathode to the anode to the base of Q1, which I don't even see in here. The current is applied and used to light up the LED. This on-off circuit useless for measuring light intensity. An LM741 at the input, at the output of a photodiode. LM358. that circuit's just too simple. It's just like an on-off switch for bright lights and stuff. I think, really honestly, I think I got what I need. Practical JFET circuits. Okay. Basic JFET constant current biasing system. Self-biasing source follower. 3819? The fuck? I want 2819. Maybe. I mean, maybe. MPF 102s. I got those too. I think they wrote the number wrong. That's supposed to be a 2819. You know, this has got a lot of stuff in it. A lot of ideas. I don't like the idea of hooking this transistor up to this FET though. I'd rather have an output where I can have some kind of control coming out of it, like these two up here. There's some different kinds of outputs there. Voltage control attenuator, DC to AC on a chopper circuit. Yeah, that's nice. There's some interesting possible design circuits that might help me with my design. I'm noticing this 2 megohm here in series, and over here there's 2 megohms kind of in parallel across this thing. They're looking for 2 megohms. It's a common number. We don't really need a lot of gain. What we need is sensitivity. So like, I could build these circuit, and then try to have a way to measure. Like, I can use the attenuator, and maybe what I should do that tonight. Let's just get a phone call pretty quick. Wait just a minute. So I really wasn't planning on doing this. I was going to look for my photodiode, but hey, you know, this is part of the whole deal. Like, if this doesn't work, my whole project is gone. I can't do it. And I've already spent like 2 or 3 weeks working on this setup and coming up with these ideas and everything. This is absolutely necessarily must have, must work. Uh-oh. Yeah, I've still got a couple of minutes left here. Got some time. So, what we have is and the other problem, there's problems with this. You got to check the noise. You have to check interference. You've got to check isolation. You got to check you gotta check the ripple voltage thing. So I'm kind of building things in a worst case scenario, like I was doing with that scope and that generator, and obviously it you know I had this um, ripple voltage come across. It's just floating everywhere. So, and I don't know, like, this FET uses a lot of voltage. Like, it's got this mega amounts of gain, and you want to use an FET, like, say you got a 1 millivolt signal and you want to crank it up to 1 volt or something like that. It's got such a high gain that you can put some components in there. You can have a built-in filter, and you can build in some other stuff, maybe even an ALC circuit, which controls the level coming in, um, to keep the noise like way down. But for me, I mean, the voltage seems to be fine. Like, I got a plus and minus 15 volt source that I need to check. And now I have a problem with this voltmeter up here, but I do have some other voltmeters. So I think what I'm going to do versus streaming looking for stuff, which is really kind of redundant, I'm just going to try to look for my photodiodes, and I'm thinking I want to work on this circuit right here tonight. I've got a generator, and I've got to figure out how to get stuff from the equipment to the breadboard without having this stupid AC hum causing an issue. It's just an issue. I have to check my power supplies. I really need a plus and minus. The FET only requires a plus supply. It looks like you can even use headphones on that second one and use 9 to 18 volts. And you can connect a headphone. Well, it's just a low impedance. Well, it says greater than 1K, you know. My idea is to take the 3819 and get a gain out of it. They said something about you want to filter, put the filter first and then amplify. Well, there's kind of a filter there. And we could actually run, we can run the circuit program now, since I got that fixed. And run some AC analysis with, with a 2N4416. This would be fun to do. So it's filter first and then amplify. That's what they said. If you amplify first, you're amplifying needless noise. If you filter first, then you can do whatever. So the frequency range of this 2819, if I go back and look at it again, they've done. Oh God, is it even in here? This goes up to a high rating. It goes up to the 100 megahertz, I think. Let me see about this one here, which is an equivalent. That's 1 megahertz, which I'm thinking was as far as I'm going to go. We could even run tests on it, you know? We could do the frequency test, AC analysis, all kind of cool stuff with that program. Oops, did I just lose something? I think I did. What the hell did I do? What's coming up on that? Yeah, I guess so. Where am I? I think I got enough to go on, really. 220 nanofarad capacitor. That's showing up in all the circuits. as an input. There's a lot of common stuff here. There's a volume control. I don't want a volume control on the preamp circuit. Definitely do not want that. Did I save this? I did. Field Effect Transistor Basics 104. Have I seen this web page before, I wonder? Way back in the day. Signal output, signal input. What is this here? Did I save this? Oh, it's the same page. Okay. Part 1. Yeah, this is your biasing stuff, your AC stuff, yada yada. Basic amplifier stuff. See, they got a resistance there with a 10 megohm resistor. Don't really know what that's all about. There's a reverse bias photodiode circuit here. Current they produce extremely small, typical conversion gains of about 0.5 amps per optical watt. Because photodiodes generate currents, I better save this too. This tells me something about them. For instance, silicon is sensitive to photons of energy higher than 1100 nanometers. That's into the infrared. However, if the photon is too energetic, it will not penetrate enough to photodiode material to reach junction. This then produces ultra bands that are specific to each diode, depending on its strength, etc. Sensitive to 200 nanometers to 1100, but others have other sensitivities. In the UV, gallium phosphide photodiodes. You know what I'm going to do? Phototransistors, photodiodes. $940. Now, see, you got a circuit like this, okay? This is a severe problem with the work that I'm trying to do. You cannot have this, because you've got so much stray capacitance, inductance, resistance, everything in here that generates this noise. You just cannot have it. This is probably for a little bit more energetics type stuff. 50 ohm loads, yada yada. Designed for low noise applications. Yeah, well, that's nice. I don't need that kind of crap. I think this is assuming a little bit more ringing. We got a ringing photodiode, possible leakage, ripple current from the LDO. Okay, that's nice. You see, they've already got problems with it. What's this here? That's no good. So I'm dead set on using a JFET amplifier in order to amplify the signal. But the question... So the light signal is going to come in, it's going to be... Well, it's going to be probably maybe 1,000 times stronger than the signal I'm trying to read. So the light itself is going to create a noise. Let's see. Is this temperature? What is this? It's intensity. Spectral. Relative energy. Daylight, incandescent, fluorescent, cool light LEDs. That's why they're saying, see, there's a lot of damaging energy in the sun. A lot of ultraviolet UV rays. Doesn't tell me phosphor-based white LED emission, power intensity. I mean, just relative energy, noon sunlight, tungsten lamp, molecular expressions. This one has something amps per microhertz. Full scale is 500 picoamps. 10 gigohm resistor Johnson noise. There's a dotted line. The blue is sensitivity. Goes down as frequency goes up. Wait, that's spectral noise density. 10 to the 0? That's 1. Oh, is that 1 teraamp or something? I have no idea. What the hell, man? Okay, here we go. Here, it's a temperature scale. Infrared. Let's see, infrared. Wow. Okay, the blue sky is 10,000 K. Basic LED rooms. Kelvin color temperature scale. It says the infrareds are cooler. The temperature goes up with the blue light. 2,000 degrees Kelvin. Wait. It's like 3,000. Well, this one is 1900. 2,000 degrees Kelvin. Then you have to figure out the noise. Let's see. Noise diode, microwave. See here. Diodes and transistor noise. Noise generator diode. The first noise generator is used with gas, or whatever the hell that shit is. Noise in 3 different bandwidths. The average. Tell me. $50 PC board. Making a noise. Minus 34 dBm. This is not what I'm looking for. I'm looking for probably just thermal noise, you know? It's a thermal noise thing. Thermal noise information, BJT noise, diode noise. It's right here, delta F. Q is charge in coulomb. Mamacita. Not very good luck, huh? I mean, it's down there, like, really. Microvolts per square root hertz. They've got different. So we're talking 3 microvolts. It's right at the range of the diode sensitivity. 10 hertz to 8 gigahertz. Like, I don't know what these are. Diodes are. It's done in a microvolt range. Oh god, I lost everything. That's my I'm advertising my webpage. So anyway, I think I should mess with that JFET circuit. Really. Get a signal. So the signal that comes in, it could be like, say it could be, we have to convert the microamps to volts somehow. Or the transimpedance amplifier thing converts the current to the voltage. All right, let me see something here. So where that is, my pictures. God, what the hell did I do with that here? Let's look. Oh, I've got to call it quits. I was just going to do a quick look at something. There's audio preamps, and then there's the transimpedance amplifier. Interesting things to look at. I might be back, I might not, but that's the plan. Is we're gonna go to the JFETs, and I'm gonna look for my photodiodes. Maybe I can do something with it tonight. I don't know.